Hello everyone. So let's now solve practice assignment week 6, question number 1. Which of the following statements are correct? So let's look at first option. There exists a linear transformation from R2 to R2 such that t of 2, 3 is equal to 1, 2, t of 1, minus 1 equal to 1, minus 1, and t of 4, 1 equal to 1, 0. So option 1. Now we have given that t of 2, 3 is equal to 1, 2, t of 1, minus 1 equal to 1, minus 1, and t of 4, 1 is equal to 1, 0. Now, if we look at these three vectors, we can say that there would be some alpha and beta for which this equation would be true, as these two vectors are linearly independent. So that means these two vectors will form the basis of R2, and by some linear combination of these two vectors, we can find any vector in R2. So that's what we are doing. And on solving this equation, we will get that 4, 1 is equal to 2, 3 plus 2 times 1, minus 1. So here our alpha is 1 and beta is 2. So now if we take t both sides, it will be t of 4, 1 and t of 2, 3 plus 2 times 1, minus 1. Now using the property of linear transformation, I can write it as t of 2, 3 plus 2 times t of 1, minus 1, and we are given t of 2, 3 as 1, 2 and 1, minus 1 as 1, minus 1. So if we put this value here, we will get 3, 0. But we are given that t of 4, 1 is equal to 1, 0, and that means 1, 0 is not equal to 3, 0. So there is no such transformation which satisfy these conditions. Hence, option 1 is false. Now option 2, if there is a linear transformation such that t of 2, 3 equal to 1, 2 and t of 1, equal to 1, minus 1, then t of xy is equal to 1 by 5 times 4x minus 5 minus x plus 4y. So option 2, again we have given that t of 2, 3 is equal to 1, 2 and t of 1, minus 1 equal to 1, minus 1. Now, as again these two vectors are linearly independent and hence form a basis. So from the same logic, I can write 1, 0 as 1 by 5 times 2, 3 plus 3 by 5 times 1, minus 1. So if I take t both sides, I will get 1 by 5 times t of 2, 3 plus 3 by 5 times t of 1, minus 1. And, and on solving this, we get 1 by 5 times 1, 2 plus 3 by 5 times 1, minus 1. So that is 1 by 5, 2 by 5 plus 3 by 5, minus 3 by 5, and we'll get 1 by 5 times 4, minus 1. Now similarly, if we go about finding t of 0, 1, it would be t of 1 by 5 times 2, 3 minus 2 by 5 times 1, minus 1. And let's simplify. T of 1, minus 1. So this would become 1 by 5, 1, 2 minus 2 by 5, 1, minus 1, and which is equal to minus 1 by 5, 4 by 5. Okay, so minus 1, 4. Now we have to find t of xy here. So we can write xy as x times 1, 0 plus y times 0, 1, taking t both sides. So it would be t of x times 1, 0 plus y times 0, 1, And again, using the property of linear transformation, x times t of 1 comma 0 plus y times t of 0 comma 1. So t of 1 0 we got as 1 by 5 times 4 comma minus 1 and t of 0 1 minus 1 comma 4. So taking minus 1 by 5 common, 4x minus y, 4x comma minus y plus minus y, sorry, 4x minus x here, minus y comma 4y, and this would become 1 by 5 4x minus y comma minus x plus 4y, and that's exactly what is given there in the option. Hence, second option is correct. Now let's look at third option. Let beta be the basis and gamma with this basis for the vector space V. Consider a linear transformation from V to V such that T of V1 equal to this, V2 equal to this, and V3 equal to this. The matrix representation of T with respect to beta and gamma for the domain and codomain respectively is this. So let's try finding it. Option 3. So we have given beta as V1, V2, and V3, and gamma is 2V1 plus V3, V2 minus V3, and V3 minus V1. So now we have to find the matrix representation for taking basis vector for the domain as beta and for codomain as gamma. For that we have given T of V1 is 2V3 plus V1, T of V2 is 2V1, and T of V3 is 2V2. Now to find the matrix representation of this linear transformation, we need to represent this image vector or image of this vector for the basis vector for the domain in terms of linear combination of the codomain vector. That is, I can write this image in terms of linear combination of these vectors from codomain as follows. As let's use that 1 times 2v1 plus v3 plus 0 times v2 minus v3 plus 1 times v3 minus v1. If we expand this form, we will get back to this image vector here, and that's everything we need to do for these two also. So this will become now 2 by 3 v1 plus v3 plus 0 times v2 minus v3 minus 2 by 3 times v3 minus v1, and for third it will be 2 by 3 2v1, sorry, here it will be 2v1 plus v3 2 times v2 minus v3 plus 4 by 3 v3 minus v1. Now as these are the bases, so we can write any vector in R3 as a linear combination of these three vectors. Now our next step to find the matrix representation is, as the dimension for the basis vector for domain and codomain are 3 and 3, so matrix would be of order 3 cross 3. That is the dimension of domain and codomain. Now next is, we will take these coefficients of these linear combination of these bases. We will take these coefficients of, let's say, the first image vector of this v1 vector and these coefficients 1 0 1 and put them column wise of this matrix 1 0 1, and same we will do for the second image, that is these coefficient 2 by 3 0 and minus 2 by 3. We will put them as the second column. And for the third also, this 2 by 3, 2 and 4 by 3. So this is our matrix representation for the linear transformation. Let's check if this is the same matrix. So 1, 0, 1, 2 by 3. So yeah, it's the same matrix. So hence third option is correct. Now let's look at fourth option. It's the same option. It's just that it is saying that the rank of the T is 3. So if the rank of T is 3, that means the rank of this matrix would also be 3. And as it is a square matrix, which is of order 3, and it can only have rank 3 when the determinant of this matrix is non-zero. So let's calculate the determinant. I will be calculating determinant along this row expansion, minus 2 times 4 by 3 minus 2 by 3. So that is minus 4 by 3. So the determinant is non-zero, hence the matrix will have full rank. So the last option is also correct. Thank you.